Imagine the International Space Station suddenly losing its electrical supply for 12 hours. The core problem is simple to state and complex to solve. Nearly every system that keeps the station habitable and operational, air, heat rejection, water recycling, communications, and attitude control, depends on continuous electric power. Understanding how astronauts survive an extended blackout requires unpacking how the station generates and distributes electricity, which systems are absolutely essential, how they can be triaged to stretch limited resources, and where the architecture itself becomes fragile. The primary electrical source on the station is sunlight converted to electricity by large photovoltaic solar arrays. These arrays are mounted on rotating mechanisms that keep the panels pointed toward the sun as the station orbits Earth. Electricity from the arrays is routed through power conditioning hardware into a high-voltage direct current distribution network. That high-voltage bus feeds batteries that smooth generation during orbital night and transient events, DC-to-DC converters that supply the low-voltage circuits used by life support and avionics, and the switching units that control which loads receive power. Batteries on board provide immediate backup when generation dips. Historically, nickel-hydrogen batteries were used, and in recent years many have been replaced with higher-capacity lithium-ion units to increase energy density and reduce cycling constraints. Life support systems depend on that electricity in multiple, interlocking ways. Oxygen is generated by electrolysis in the US oxygen generation system and by the Russian Elektron system. Both require steady electric power to split water into oxygen and hydrogen. Carbon dioxide removal is performed by sorbent-based or regenerable systems that use fans and valves to cycle air through adsorbent beds. The US Carbon Dioxide Removal Assembly, CDRA, and the Russian Vozdukh are examples. Water processors, wastewater reclamation, and the internal water loops that redistribute heat and provide potable water depend on pumps. Cabin air mixing uses fans to prevent local pockets of CO2 or thermal stratification. Thermal control is active. Heat generated by electronics and by crew metabolic loads is transported through internal water loops to external ammonia loops and radiated into space via heat exchangers. Attitude control, keeping the station oriented so the arrays track the sun and so structural loads remain within design limits, is primarily done by electrically driven control moment gyroscopes, CMGs. Thrusters are a secondary system used when CMGs saturate or are unavailable. When electrical supply falls to near zero, the station is not uniformly plunged into immediate catastrophe because it was designed with layered redundancy and operational modes. The first response is automated protective logic, non-essential loads are shed, and priority buses are isolated to preserve power for critical functions. Crew procedures define a survival or degraded configuration. Instruments and experiments are powered down, crew quarters lighting and non-critical outlets are turned off, and consumables are minimized. Critical loads that must remain powered include minimal ventilation and CO2 scrubbing to prevent rapid buildup, basic heating to prevent freezing of water-bearing systems, communications for command and telemetry, and equipment that maintains pressure integrity. Batteries extend available energy into short blackouts and orbital nights. For longer outages, multiple strategies are used in combination. First, load prioritization reduces consumption to a few kilowatts for essential life support and command and control. Second, alternative oxygen and CO2 strategies come into play. Pre-stored gaseous oxygen tanks and emergency oxygen resupply bottles provide breathable air if electrolyzers are offline. Passive means of CO2 adsorption, such as spare canisters of lithium hydroxide or modular solid sorbents, can be used to supplement or temporarily replace regenerable scrubbers. Thermal inertia of the station's mass buys time. Structural materials, equipment racks, and stored water act as thermal buffers that slow the rate of temperature drift when active heating or refrigeration is lost. There are, however, critical constraints and a number of weak links that make a 12-hour outage significant. First, battery capacity and state of charge set a hard limit on how long critical loads can be supported without generation. Batteries are sized for expected eclipse durations and routine contingencies, not for prolonged, system-wide generation loss. If the arrays are unable to generate because they are misaligned or because the power conditioning units have failed, batteries deplete rapidly once essential loads are maintained. Second, life support hardware often requires continuous operation to avoid damage or to preserve efficacy. Water processors and pumps, if abruptly stopped and then restarted after a prolonged cooldown, can suffer cavitation, seals may fail, and biofilms can expand in unexpected ways. The CDRA uses temperature and pressure cycles in its sorbent beds. Unplanned shutdowns can upset cycle timing and degrade scrubber performance when restarted. The oxygen systems generate hydrogen as a byproduct. That hydrogen must be vented or reacted safely. If electrical control of venting systems is compromised, hydrogen accumulation becomes a safety hazard. Thermal control presents a nuanced trade-off. Active heat removal pumps are electrical. Without them, heat from electronics and humans accumulates locally and can cause overheating. Conversely, in shaded or cold orientations, lack of heating can allow fluid lines in external loops, or even internal water in radiators and storage, to cool and risk freezing. Ammonia used in external loops is particularly sensitive. It must remain molten and circulating to transfer heat from internal systems to external radiators. If pumps stop and external temperatures are low, ammonia can localize and freeze or cause two-phase flow issues that complicate restart. The station's inertial mass and insulation provide a buffer, but the acceptable window before temperature-sensitive components reach operational limits is measured in hours, sometimes less for particular subsystems. Attitude control is a decisive dependence that illustrates cascading failure modes. Control moment gyroscopes require electrical power. If CMGs lose power and thrusters are used as a fallback, that consumes propellant and requires active precision. Propellant is a finite consumable. If both gyros and thrusters are unavailable, the station can begin to tumble slowly. A tumbling station cannot keep solar arrays pointed, the thermal balance is disrupted, and communications antennas may not maintain line of sight to relay satellites. A single failure in electric power can thus propagate into a loss of generation, a thermal emergency, and a communications blackout. Moreover, certain margins were chosen assuming crew and ground can intervene. A simultaneous communications outage complicates recovery. Segmental architecture provides both resilience and complication. The Russian segment has its own arrays and generators and can operate semi-independently. Cross-segment power transfer exists but is limited by interface capacity and control complexities. Visiting vehicles docked to the station can carry consumables, oxygen, water, and sometimes spare filters, and in some configurations can provide short-term power or communication relays, but they are not designed to replace primary station power for extended periods. Operationally, ground teams can send commands to reconfigure power routing, disable non-critical loads, and prepare consumable deployment, but that presumes communications are available and that software and hardware are responsive. Human physiological and psychological limits add another constraint layer. Carbon dioxide toxicity, even at modestly elevated levels, impairs cognitive function and can become life-threatening within hours if scrubbers fail and alternatives are exhausted. Temperature drifts outside comfort ranges reduce metabolic efficiency and make manual intervention more error-prone. Crew mobility and ability to perform tasks is dependent on lighting and powered tools. Handheld battery tools can bridge some needs but not the systemic requirements. Considering edge cases sharpens the architectural vulnerabilities. A failure mode in which attitude control is lost while the array's gimbal motors are also unresponsive is particularly pernicious. Even if arrays are illuminated, they may not be oriented to generate useful power. A software fault that causes erroneous automatic load shedding might isolate batteries or critical buses themselves, preventing even local power use. Single-point mechanical failures in pumps or valves that cannot be actuated manually because their actuators are electrically commanded create hardware traps. The interactions between chemical processes, hydrogen from electrolyzers, CO2 scrubbing chemistry, and water reclamation can lead to cascading resource imbalances if one subsystem is unavailable for an extended interval. The engineering trade-offs are clear. Increasing redundancy and capacity, larger batteries, duplicate power converters, more cross-strapping between segments adds mass, complexity, and integration cost. Passive systems that do not require electrical power for critical survivability, passive thermal radiators, mechanical valves that can be set manually, architectures that allow CO2 to be passively sequestered, reduce dependency but have limited efficacy in the small volume, high-performance context of the station. Forward-looking challenges remain. Designing an orbital habitat that can tolerate multi-day power loss without ground intervention would require rethinking the microgrid, power electronics that are fault-tolerant and self-healing, energy storage that is safe at high energy density and capable of deep discharge without degradation, and architectures that enable asymmetric cross-feeding between modules irrespective of segment origin. Autonomous fault detection and reconfiguration algorithms that can safely isolate failed components and reroute power without human in the loop are needed to prevent transient faults from becoming station-wide outages. Hybrid power approaches integrating fuel cells for temporary high-density energy, or compact radioisotope thermoelectric generators for low but persistent power, could provide an independent baseline for essential functions such as CO2 control and minimal heating. Advances in passive life support technologies, high-capacity sorbents that operate at ambient temperatures, thermal systems that combine phase-change materials for buffering, and mechanical backups for critical valves would reduce the hourly consumption burden during outages. A specific unresolved engineering question is how to balance mass and complexity against survivability. What is the optimal subset of systems that must remain powered to preserve life and hardware, and how can those systems be backed by truly independent, low-mass energy sources? Creating a lightweight, fault-tolerant microgrid for crewed spacecraft that survives purposeful and accidental multi-day blackouts without mission-ending risk remains an open problem at the intersection of power electronics, materials chemistry, and autonomous systems engineering.